Welcome students. In this session we are going to discuss the basics of the engineering materials and metal casting, metal welding and metal forming, and all the basics should be covered in this session. So the problem session will be handled by another shop, and you can follow the basics. We will discuss now. Welcome to the class. So now we are going to see about the material science. In material science, the first topic is change of phase means either there is a change of microstructure or change of lattice structure. When the phase change take place means the microstructure will be changed or lattice structure will be changed. So a phase diagram is represent the temperature as it ordinate alloy composition at the abscisse and Curie point. What do you mean by Curie point? Curie point is there is no change in phase. The phase may not be changed, but only magnetic properties are disappearing. The point at which the phase does not change and magnetic part disappearing is termed as Curie point. So based on that, we are having three material: diamagnetic material, paramagnetic material, ferromagnetic material. In diamagnetic material, the electrons are unpaired, such alloys exhibit colors. So in the paramagnetic material, electrons are unpaired, such alloy exhibit color. In diamagnetic material, electrons are paired and such alloys are colorless. And ferromagnetic material, iron behaves as well as paramagnetic and diamagnetic. So diamagnetic material has small and negative value of successibility, paramagnetic material and small and positive value of successibility, ferromagnetic material has large and positive value of successibility. So the material can be classified as amorphous structure or crystalline structure, mesomorphous structure. Amorphous structure means the atoms are chaotically arranged, and crystalline structure means it has arranged in the definite order. Mesomorphous means it may varies, it regularly in some direction and chaotic in other direction. Next, crystal structure. Types of crystal structure we can see: cubic, tetragonal, orthogonal, hexagonal, rhombohedral, monoclinic, triclinic. So here we have to consider the relation between the primitives and interface angles. So you can observe, if for cubic all the sides are equal, and interface angle all the angles are equal to 90 degree. So iron, aluminium, copper are come under the simple cubic system. Then tetragonal, one side is not equal and angle all are equal to 90 degree. For tetragonal, tin is a very good example. For orthogonal, all the sides are not equal and all the sides are not equal. So we are having alpha equal to beta equal to gamma equal to 90 degree. So in hexagonal, A equal to B equal to not equal to C, but one angle is 120 degree. So for hexagonal, silicon dioxide, silver chloride are the very good example. For rhombohedral, rhombus means all the sides are equal, but all the angles are equal, but is not equal to 90 degree. So calcium sulfate and calcium carbonate are the example for the rhombohedral. Monoclinic, all the sides are not equal. Triclinic, all the sides are not equal. So but in monoclinic, two angles are equal to 90 degree, one angle is not equal to 90 degree. So gamma value is not equal to 90 degree. In triclinic, all the angles are unequal and not equal to 90 degree. So we are having simple cubic cell. Simple cubic, we can have each atom, the corner will be shared by the 1/8 of the atom. So it has to be the total number of atom present in the simple cubic structure is 1, and atomic vacuum factor is the volume of atoms in the cell to the top volume of unit cell. So when you calculate, you can get atomic vacuum factor as so you can get 0.52. When it is mentioned in percentage, 52%. So at void, to calculate void, it is 100 minus the percentage of atomic vacuum factor, it is 48%. So in crystal structure, the arrangement of atoms in crystal is called as crystalline structure. The lattice structure of the particular metal is shown by the smallest group of atom is known as unit cell. This lattice structure is named as unit cell. Crystal structure can be called as crystalline structure. So for the body center cubic, the atomic packing factor can be calculated as 68% and percentage of voids can be calculated as 32%. The number of atoms in the units, the number of atoms in the body center cubic is 2 because in center one atom will be there and in each corner 1/8 atom will be there, so its value is 2. For face center cubic, it can be calculated. For face center cubic, it can be calculated. The number of atoms in the unit cell is 4. The number of atoms in the unit cell is 4 because all the corner one atom will be there and in all the faces half of the atom will be shared. So 6 into half 3. So 1 plus 3 4. And the radius is R equal to A divided by 2 root 2 in the face center cubic, and atomic packing factor is 0.74. When it is mentioned the percentage, it is 74% and percentage of void is 26%. Next we are having the examples and the coordination number and atomic packing factor are comparatively mentioned here. In simple cubic we are having coordination number is 6, that is we are having 6 neighboring atom. For a single atom, it has a 6 neighboring atom. It has a 6 neighboring atom in the single cell. So we are having, so in simple cubic, so for each atom we'll have to face 6 atoms. So it is top, bottom, on the side 4, and so it has 6. So for body center cubic it is 8. For face center cubic the coordination number is 12 and HCP 12. So this thing we already discussed. It is atomic packing factor in the terms of fraction. So we are having 3 different types of bond: ionic bond, covalent bond and van der Waals bond. Van der Waals bond is the weakest bond. This covalent bond is the strongest bond. So ionic bond is formed between the transfer of electron between the atoms. So sodium chloride, it is a primary bond. Ionic bond is called as primary bond. Covalent bond is it is in chlorine Cl, this is the covalent bond. Covalent bond or electrons are shared. Here electrons are transferred. Van der Waals bond is the weakest bond. It can also called as dispersion bond, dipole bond, hydrogen bond. So molecular bond all are belongs to the van der Waals bond. So van der Waals bond is the weakest bond. So we are having the properties. Properties means ductility is a large permanent deformation under tension. When you give the tension, the deformation take place, it is called as ductility. Malleability means when you give the compression, deformation take place, it is called as malleability. Deformation under compression is malleability. Deformation under tension is ductility. Ductility is important in the case of wires. Malleability is important in the case of sheets. So hot hardness is the property of resisting softness at the high temperature. Hot hardness is nothing but it has to resist the softness at high temperature. Creep is the progressive deformation take place. It is the progressive deformation take place under constant load. The load should be constant and at elevated temperature with respect to time. It is a time dependent phenomena. That is a progressive deformation take place at the constant load at elevated temperature with respect to time is termed as creep. It is slow plastic deformation. So material can be classified as homogeneous material, heterogeneous material. Homogeneous material means it has same composition at a different point. So this is the point A and this is the point B. At all the point that is same composition, then the material is called as homogeneous material. Homo means same, genus means composition. So same composition means homogeneous material. Different composition at different point means heterogeneous material. And we are having isotropic material. Isotropic is a directional property. In all the direction, the product has the same property. It is called as isotropic material. In different direction, different properties mean anisotropic material. And viscoelastic property is the time-bound behavior. It can be observed in the non-crystalline organic polymer. So when we see the stress-strain behavior of the mild steel, it is a linear, and for rubber it is non-linear. For rubber it is a non-linear, mild steel is a linear. So we are having types of iron: cast iron, wrought iron, grey cast iron. So for cast iron, the damping characteristics is important. For wrought iron, corrosion resistance is important, and the grey cast iron, machinability is significant. So these are the unique features. So you can see the ferrite. It is a microstructure which has the 0.025% of carbon, and it can be also called as alpha iron, and it is in the form of BCC structure. The austenite has 1.7% carbon, and it is in the form of FCC structure. So austenite, FCC structure, ferrite, BCC structure. So we are having some product and material. So wheel and axles of tractor is made by plain carbon steel. Wire, rivet are made by mild steel. Tin can is made by mild steel. Machine tool bed, the lathe bed is made up of grey cast iron. And skate roll, we are skating on the roll, that is made up of medium carbon steel. So leaf spring is made up of high carbon steel, and automobile radiator is made by yellow brass. Heating element, we are using the heater, it is made up of nichrome or chromal. And the rail, the train move on the rail is made up of medium carbon steel. Musical wire, it is made up of alloy steel. And ball bearing, this ball bearing is made up of carbon chrome steel. So bulldozer blades are made by addified manganese steel. So we can know that some of the alloys application. White metal is used for bearing liners, and the constant 10, the thermocouple, the constant 10, the metal used is constant 10, and the carbon chrome steel is used in the ball bearing. Low carbon steel, wire nails are applicable. Addified manganese steel, bulldozer blades. And Elinvar is used for precision instruments, because Invar has zero thermal coefficient of expansion. It does not expand under the elevated temperature. And Admiralty brass, steam condenser tube, nichrome, heating element. So these are some of the application we have to found in day-to-day life. So next we are going to see about the alloy composition. The alloy compositions are bronze. It is 90% copper and 10% tin. So bell metal has 75 copper, 25 tin. So instead of, when you compare bronze and bell metal, here copper value is less. Aluminum brass, 90% copper and 10% aluminum. Silicon bronze has 96% of copper, 3% of silicon and 1% of manganese. Beryllium bronze has 98% of copper, 2% of beryllium. So brass, next we come to discuss about the brass. Brass is the alloy of copper and zinc. You can see in brass itself the name, the letter S will come. So copper plus zinc. Here Z will come. In bronze you can observe in the letter Z will come. Here copper plus tin. So you can easily remember. One here Z come means here S. Here S in brass S is there, and copper Z will be there. So you can easily remember. In brass contains, it is 70-30 because number of letter is less here. In bronze contain, it is 90-10. So letter will be 6 letter word, here 5 letter word. For 5 letter word, copper less composition. For 6 letter word, it is more composition. You can easily remember the amount of copper in brass and bronze. Okay, next duralumin. Duralumin is 94 aluminum and 4 copper, remaining magnesium, manganese, silicon, copper. Next gunmetal. Gunmetal is 88, 10, 2. Here 2 is lead and nickel, 10 is tin. 88, 10, 2. Admiralty gunmetal, 88 copper, 10 tin and 2% zinc. Bunz metal, 60% copper and 40% zinc. In German silver, there is no silver, only copper, nickel, zinc. Copper is 60, zinc is 35 and nickel will be 5. Inconel consists of 6% of iron, 80% of nickel and 14% of chromium. And Constantan is the copper nickel alloy, it is 60% of copper and 40% of nickel. And yellow alloy consists of 4% of copper, 2% of manganese and 2% of nickel, and silicon, manganese and iron are 0.6% and remaining is aluminum. White metal, lead, tin, cadmium. So babbitt, tin, copper, antimony. Monal metal, it is also a copper and nickel where copper is lesser percentage. And perm alloy is a iron and nickel alloy. Delta metal, copper, zinc and iron. So solder is nothing but it is a lead and tin composition. Solder is lead and tin. This is the solder, and it is used in the soldering process. And you should know about the spelter. Spelter is used in the brazing process. In brazing we are using spelter. In soldering we are using solder. Both are filler metal. Solder is a filler metal in soldering. Spelter is a filler metal in brazing. So here copper and zinc. So in spelter it is copper and zinc, in soldering it is lead and tin. We are having some of the solder, lead and tin and antimony. Silver solder, silver, copper, zinc, and for phosphorus bronze it contain no phosphorus. And Dow metal, it is magnesium, aluminum, copper. Stellite is a non-ferrous cast alloy. We can remember by Crow. So it is a non-ferrous cast alloy. So these are some of the significance. Invar is zero thermal coefficient of friction and expansion. Brass, it quickly work harden. Brass, what is the properties of brass? It quickly work harden. So next is steel, type of steel, low carbon steel, medium carbon steel, high carbon steel. In low carbon steel, the carbon percentage is less than 0.25%. This is low carbon steel. And medium carbon steel, it is carbon percentage lies between 0.25 to 0.5. In high carbon steel, it is 0.5 to 1.5%. So in that way the steel can be classified into low carbon steel, medium carbon steel and high carbon steel. Next we should know about the elements to be added to steel to get the particular property. For carbide formation, it is chromium, tungsten, titanium, vanadium, manganese and molybdenum. For cementite formation, sulfur can be added. For graphite formation, it is cobalt, silicon, nickel and aluminum. And arsenic stabilizer, it is manganese, nickel, cobalt and copper. And ferrite stabilizer, it is chromium, tungsten, molybdenum, vanadium and silicon. For corrosion resistance, it is an important thing. Chromium is the important thing. For fatigue resistance, we add nickel. For impact resistance, we add vanadium. For elasticity, we add tungsten. These are the alloying element added for the steel to get the required property. For brittleness, we should add nitrogen. For hardness, we should add tungsten. For hardenability, it is manganese, molybdenum, vanadium. So our trivalency element are act as a deoxidizer. Aluminum is trivalency, boron, chromium, vanadium and silicon silicon, manganese, zirconium, all are trivalent, so it can be used for deoxidizer. For magnetic property, we can add silicon. For strength, nickel, tungsten, vanadium. For mechanical property, zirconium and boron. For welding property, we can add niobium. For forced temperness, we can add boron or molybdenum. For airline cracks, we can add hydrogen. For grain growth inhibitor, we can add aluminium. And red hotness, for red hotness, cobalt, molybdenum, tungsten. For hot shortness, sulfur. For cold shortness, phosphorus. High temperature strength can be obtained by chromium. So it is a copper alloying element. For copper added with nickel, it raises the hardness. Copper added with lead, it produces free machining properties. Copper added with silicon increases strength. Copper added with beryllium, non-magnetic and non-sparking alloys. So for the aluminium, when we add with silicon, it improves the castability. For aluminium, when you add lead and bismuth, it increases the machinability. For aluminium, the manganese improves the corrosion resistance. Steel is added with lead, phosphorus, sulfur. When you add any one of these, so it will increase the machinability. Next, how the steel is specified. Types of steel. Adified steel means when it is 12% of manganese is there, it can be called as adified steel. And it can be 2XX means it is nickel, 3XX means nickel chromium, 3213 means stainless steel, 31XX means adified, 4XX is molybdenum based steel, 5XX means chromium. So these are the different specification you should be remembered while designation of steel. Next, types of cast iron. Cast iron is when it is 2% of carbon. When the iron has less than iron plus 2% of carbon gives up to 2, it is steel. When it is greater than 2 to carbon percentage is 2 to 6.63%, it will form the cast iron. So for cast iron, it is from 2 to 6.63. For steel, it is up to 2%. And we are having different types of cast iron. One is grey cast iron, another one is white cast iron. The next is mottled cast iron, then malleable cast iron, inoculated cast iron. So we will see one by one. In graphite cast iron, it has poor tensile strength. The graphite is in the form of flakes. The specific feature is graphite in the form of flakes. In white cast iron, graphite in the form of cementite phase. In mottled cast iron, it is a mixture of grey and white. Mottled means mixture of grey and white cast iron. Malleable cast iron means it is produced from the white cast iron, heated for long time and slow cooling. It decomposes the ferrite. So because of this, malleable cast iron can be produced. Next is spheroidal cast iron, that spherical models are formed. Graphite are absorbed in the form of spheres. Inoculated cast iron, we have to molten pig iron by the silicon. It can be produced. Silicon compounds such as calcium silicate is added, then it is called as inoculated cast iron. Next we are going to see the grey cast iron. Grey cast iron, the carbon is form of free flake, and white cast iron, it is combined form. Chilled cast iron, there is no graphite is there. Ductile cast iron, or it makes the nodular cast iron or spherical cast iron, malleable cast iron. So when the graphite is having lower density, it is called as KISH, due to which it comes over the surface of liquid iron in the red dot condition. During red dot condition, it will convert into KISH. Next thing we are going to see about the Gibbs phase rule. It is used to find the degree of freedom of the component of the system, that is equal to D equal to C minus P plus 2. So where D is the degree of freedom, C is the number of component, and P is the number of phase. So this is a two component system. It depends on two variables. It can be plus 2. Now we are going to know about the different microstructure. Here austenite. Austenite is the soft, ductile, malleable and non-magnetic. Austenite is the soft, ductile, malleable and magnetic. And perlite. Perlite is the 13% of cementite and 87% of ferrite, and 6.3663% of carbon consists of cementite. Cementite is the hardest phase in the iron carbide diagram. And we are having martensite. Martensite has the maximum hardness. So martensite hardness is 65 HRC. You can remember by martensite 65. Okay. Next is spharodite. Spharodite is found from quenching austenite. Sorbite is found by quenching austenite. Trucite is found by quenching austenite. But here the heating temperature varies. So you can see, observe here 200 to 375, 375 to 660, and 660 to 700. So spharodite lower temperature, sorbite somewhat higher temperature, and trucite it is somewhat higher temperature. The heating temperature varies, the structure obtained is varies. So all these things are obtained by quenching austenite. So we should have fine grained steel or ductile in nature, coarse grained steel or brittle in nature. Okay. So austenitic stainless steel is having FCC gamma n plus 0.2% of carbon in solid solution. Next we are going to know about the hypoeutectoid steel, hypereutectoid steel, hypoeutectic cast iron and hypereutectic cast iron. So we are having one line here, so we can demarcate. So this is 0.8 up to 0 to 0.8 it is hypoeutectoid steel. Up to 2 it is hyper means high. Hypereutectoid steel, and up to 4.3 it is hypoeutectic cast iron, and after that hypereutectic cast iron. So this is the range. So we are having hypoeutectic cast iron and hypereutectic cast iron, hypoeutectoid steel and hypereutectoid steel. At the exact point it can be called as 0.8 is called as eutectoid steel, and 4.3 it is called as eutectic cast iron. That is eutectoid steel, here eutectic cast iron. So you can observe here, it is less than 0.3 means 0.83 is hypo means less, greater means hyper, 0.83 up to 2 steel, after 2 cast iron. So after 2 cast iron, hypo means lesser, hyper means 4.3 to 6.63. Eutectoid mixture is a mixture of ferrite and cementite. Eutectic mixture is a mixture of austenite and cementite. So ferritectic is the FCC gamma n plus 2% of carbon in solid solution. That is a ferritectic austenite. Okay. We are having 3 different types of stainless steel. One is austenitic stainless steel, and another one is martensitic stainless steel. So, and ferritic stainless steel. Ferritic stainless steel always have the properties of corrosion resistance. Austenitic stainless steel hardenable only by cold working. Martensitic stainless steel hardenable by heat treatment. So these are the main. It has the machinability. Ferritic stainless steel has good machinability. Austenitic stainless steel magnetic in annealed condition, and martensitic stainless steel has good thermal conductivity. Next we are having the different heat treatment process. In heat treatment process, annealing means heating. First we are going to heat and cool within the furnace. Normalizing heating, cool in the presence of air. Hardening is a process of heating and cool by means of quenching medium. Tempering is the process where heating and cooling repeatedly, heating and cooling repeatedly and slowly. Heating and cooling, we have to heat and cool repeatedly and slowly. So annealing is process in which it has to be cooled within the furnace. We have to switch off the furnace after heating. We have to switch off the furnace. There cooling take place. Full annealing produce the ductility and toughness. Process annealing produce the stress relieving. Spheroidized annealing increase the machinability. Diffuse annealing homogeneous the chemistry of the material. Okay. So in normalizing, what we are doing, we are heating the furnace and it has to taken out and keep it in the presence of air. Hardening, we are heating the furnace and quench in a medium. It may be water, oil or brine solution like that. Here you should remember one thing, only medium carbon steel are hardened. Tempering, after hardening, it produces a needle structure. So after hardening, we always do tempering operation to increase toughness, to reduce brittleness, to increase ductility. This is the 3 points you should remember for tempering operations. Next is, we are going to know about the Mars tempering and Haas tempering. Haas tempering means we have to make what happen, it has to be bayonet structure is formed. So here we have to heat above the upper critical temperature and cooled. It has to be cooled in, it has to be quenched in isothermal quenching. What do you mean by isothermal? Isothermal means constant temperature. Isothermal quenching, by the way of isothermal quenching, we are getting the structure called bayonet. In Mars tempering, what happens? In Mars tempering, what happens? Subsequent quenching. It is heated above the upper critical temperature and subsequent quenching. What do you mean by subsequent quenching? Subsequent quenching, two medium. It has to be quenched in one medium and it has to be quenched in other medium. Quenching medium 1 and quenching medium 2. Subsequent quenching. So in Mars tempering, it is a two-stage quenching. Here only bayonet structure, here bayonet and Martin stick structure. So bayonet has the higher toughness, martensite has the higher hardness. So here toughness also increase, hardness also increase in Mars tempering. In bayonet only toughness is increased. So we can remember in Haas tempering A, B, T. What do you mean by ABT? It is a partial service. So we can easily remember A for Haas tempering, B for bayonet and T for toughness. You can cumulatively remember those words. Next we are having the case hardening process. In case hardening process, so we are having carburizing, nitriding, cyaniding and flame hardening, induction hardening. In carburizing, so the component it has to be hardened. So the component it should be put in the carbonaceous atmosphere. In nitriding, it is put in the ammonia gas is passed. In cyaniding, it has to take the cyanide bath. So some cyanide solution should be there. In flame hardening, we have to heat with the help of flames. So with the help of flames. In induction hardening, it has to heat with the help of coil. So if it is heat with the help of coil, it is an induction hardening. If it is heat, it is a flame hardening. So in the flame hardening, after heating, we have to quench it. In induction hardening, after heating, we have to quench it. In carburizing, nitriding, cyaniding, there is no need of quenching. So in carburizing, we have to put it in the carbonaceous atmosphere. Pack carburizing, charcoal. Liquid carburizing, sodium cyanide. Gas carburizing, methane gas. For nitriding, we are using the ammonia atmosphere. Ammonia gas is passed. For cyaniding, it is a sodium cyanide. For flame, we are mostly using the three different types of flame: carburizing flame, neutral flame, oxidizing flame. It has to be heated with the help of flames. So these are some of the points it has to be remembered. In what is the difference between heat treatment and case hardening? In heat treatment, the entire part property is changed. In case hardening, what happens? Only surface, periphery, only external surface is hardened, and internal surface, the core remains same, case is hardened, case hardness is increased, core hardness remains same, core property does not change, so because of that this process is called as case hardening, Now we are having different types of defects in material. So defects are classified into 3 types: point defect, surface defect, volumetric line defect, and the volume defect is also there. So point defect comes for vacancy defect, interstitial defect, substitutional defect, Frankel defect, Schottky defect. These are the defects come under the point defect. Surface defect, in the surface defect we are having grain boundary defect, twin boundary defect, tilt boundary defect, and staking fault. So in line defect we are having 2 line defect. One is edge dislocation, the another one is screw dislocation. In edge dislocation the Burger vector is perpendicular to the direction. In screw dislocation the Burger vector is parallel. In screw dislocation the Burger vector is parallel to the dislocation line. So we are having 2 types of dislocation: edge dislocation where Burger vector is perpendicular, in screw dislocation the Burger vector is parallel. Next is powder metallurgy. In powder metallurgy we are having powder production process. So in powder production process can be atomizing, by using the atomizing. So next is blending, where in blending what we are doing, we are mixing the powder, and the compaction we are providing the particular strength, and sintering is the heating process, and after that finishing process. So we are having next post sintering operation is impregnation. So during impregnation what we are making the porous bearings can be made by impregnation. This impregnation is the post sintering operation. So next thing we are going to see is welding. Welding is a metal joining process in which 2 similar or dissimilar metals can be joined with the help of heat or pressure or both. So it is a material joining process. So we can application of pressure, heat or pressure. So in advantage, different material can also be welded. Welding can be done anywhere. In disadvantage, heat affected zone. This is the main thing we have to concentrate in welding. So when you weld, the welding metal is called as parent metal. So if it is welded is in this region, so some of the area are heat affected zone. So that is a disadvantage. To dismantle we have to break the weld. Initial investment is more and high skilled operator is needed. This is a disadvantage of welding. An advantage, any material can be welded. And types of welding. We are having autogeneous welding, homogeneous welding, heterogeneous welding. So as already I mentioned, the metal to be welded is called as parent metal. The metal to be filled is called as filler metal. So this is the filler metal and this one is the parent metal. So if parent metal and filler metal are same, where the metal here M is used, here also M is used, means same, means homogeneous welding. When parent metal and filler metal are different, it is called as heterogeneous welding. When there is no filler metal is there, it is called as autogeneous welding. So we are broadly classify the welding as 2 types: fusion welding and plastic welding. In fusion welding, the metal is joined in the molten state. In pressure welding, the parent metal has to be converted into plastic state and the external force is applied to make it joint. So that is the plastic welding or pressure welding. Fusion welding, the metal has to be joined in the solid state. So in fusion welding, what happens? The parent metal in the form of, while joining, it should be in the molten state, where in pressure welding it would be it is not in the molten state, it is in the plastic state. Okay, so this is plastic state means pressure welding, molten state means fusion welding. So it is a broad classification. Next you can see the tree diagram for the welding. The welding can be solid state, liquid state and solid and liquid state. Solid liquid state. So in solid state we are having cold welding, friction welding, diffusion welding, forge welding. So you can, so in cold welding it is pressure welding, explosive welding, ultrasonic welding. In liquid state welding or fusion welding, the liquid state welding or fusion welding, we can say that it is arc welding and thermite welding, arc welding, gas welding, thermite welding. Okay, in liquid state, arc welding, gas welding, thermite welding, and separately resistance welding is there. So the arc welding is flux cored arc welding, shielded method arc welding, and submerged arc welding. Those are the three types. Okay, so this is a broad classification of the welding, and again we can classify fusion welding or pressure welding. In fusion welding we can get arc welding, gas welding, thermite welding. In pressure welding we can get resistance welding, forge welding. Okay, resistance welding, forge welding. So these are the broad classifications of, so pressure, under pressure welding these two come, under fusion welding these three things will come. So the corresponding temperature is given, please make a note. So gas welding 3500 degrees Celsius, thermite welding 2700 degrees Celsius, arc welding 5400 degrees Celsius, resistance welding it is higher temperature, and forge welding 1350 degrees Celsius. So these are the different joints, types of butt joint, lap joint, corner joint, T-joint, edge joint. So you can see the flat joint, vertical joint, horizontal joint, overhead joint. Welding terms, you can observe the fusion zone here, weld face here, and the angle of convexity you can observe here. Reinforcement, this is the reinforcement. And this one is the penetration, this area is called as penetration. This one is the base metal. You can observe the root face here, this is called as root opening. You can know the terminology: root opening, root face, penetration, base metal, fusion zone, weld face, angle of convexity, and reinforcement. These are the observations in this diagram. Dilution is the ratio of area of penetration to the top sum of the area of penetration and area of reinforcement. That is called as dilution. So in gas welding, what is the principle we are having? We are mixing oxygen and acetylene to develop the heat. Okay, so those we are having oxygen cylinder here, acetylene cylinder here, it has to be mixed and pass through the nozzle, the weld can be achieved. So usually oxygen cylinder in black in color, acetylene cylinder in maroon in color, and for complete combustion the ratio required is acetylene plus supplied oxygen and atmospheric oxygen are in the ratio of 1:1:1.5, and the oxygen to acetylene ratio is 2.5:1. So we should know that oxy-hydrogen flame produce 2400 degrees Celsius, oxy-acetylene flame produce 3500 degrees Celsius. So we came to know that oxy-acetylene flame produce higher temperature. So there are three types of flame. One is neutral flame, the next is carbonizing flame, other one is oxidizing flame. What is the difference? We have to see. In all the three, the oxygen and acetylene ratio, acetylene and oxygen ratio is, so oxygen and acetylene ratio is here 1:1. Here in carbonizing flame it is 0.9:1. In oxidizing flame it is 1.2:1. So A always 1, but oxygen is equal means neutral flame, oxygen is higher means oxidizing flame, oxygen is lower means carbonizing flame. So oxidizing flame is used for copper and copper alloy. This carbonizing flame is for medium carbon steel and nickel, and cast iron and mild steel. This neutral flame can be used. So this is a ratio already we have discussed, 1.5:1 and 1:1 and 0.9:1. So it can be used for here only two zones are used. Here in neutral flame 2 zones are observed. In reducing flame we are having 3 zones. In gas cutting we are always using the oxidizing flame. So next we are moving to the arc welding. In arc welding, the electrode is using to create the arc, and the electrode is coated with some material. That material is called as flux. The flux is used to permit perfect cohesion and to remove the oxides of metal as slag. So we are having the relation desired duty cycle to the top rated duty cycle equal to rated output current square to the top desired output current square. So duty cycle is inversely proportional to current square. You should remember this formula. And number of poles and speed of rotor are related by F equal to NP by 120. So we are having two different types of welding, TIG welding and MIG welding. In TIG welding, they are using non-consumable electrode. In MIG welding, they are using consumable electrode. Next we are going to know about some of the important thing in the welding. This electric arc is formed due to the contact resistance. The main criteria to select the electrode is thickness. Based on thickness of material only we are selecting the electrode. The next thing is, with the increase in the thickness of material, the current also increases. Thickness increases, current increases. So eyes has to be safeguarded by against the infrared rays and ultraviolet rays. So we are using the shield in welding. In overhead welding, the metal transfer is dip transfer. In metal arc welding, it is a molecular transfer. Molecular attraction. In metal arc welding, it is molecular attraction, and overhead welding, metal is transferred by dip transfer. Next we are going to discuss about the polarity in the welding. What do you mean by polarity? It is a negative and a positive where it is connected. If it is negative, is connected to the electrode, and workpiece is connected to positive, it is called as straight polarity. When it is reverse, reverse means electrode positive, workpiece negative means it is the reverse polarity. And in DC we are having electrode positive straight polarity, electrode negative reverse polarity. So what, and AC there is only one thing. And in heat generation here workpiece is less heated. Electrode positive means so workpiece is, this is electrode positive means reverse polarity, electrode positive means reverse polarity, electrode negative means straight polarity. So this is the, here the workpiece is heated 2/3. See here, the heat generation is 1/3. So metal deposition rate is high in, metal deposition rate is high in electrode positive, that is reverse polarity. Here it is low, in AC it is intermediate. Thickness of the work is reverse polarity thin sheet, straight polarity thick sheet, AC is intermediate. And the arc stability is easier in reverse polarity and easier in the straight polarity, but in arc stability is difficult in AC. Arc stability is difficult in AC. So arc blow is severe in DC but insignificant in AC. So these are the major things we have to concentrate as per the polarity. We are having in manual metal arc welding, we are having 40 to 100 volts as open circuit voltage and arc voltage 20 to 40 volts. The temperature produced is approximately 6000 degrees Celsius. You are observing the shielded metal arc welding where the flux coating is there and electrode is inside, the direction of travel is given, it is backward, and after welding you can observe the slag coating. So slag can be removed by the chipping action. So the function of flux is flux gives alloy to the bead material and bead becomes stronger, even the parent metal. So it controls the weld full viscosity and arc stabilization also achieved by the flux, and it protects the bead from the atmosphere. So these are some of the points you should be remembered for the flux. Now we are going to discuss about the MIG welding, TIG welding. MIG welding is the metal inert gas welding, TIG welding is the tungsten inert gas welding. So in MIG welding, what we are using consumable electrode. In TIG welding, what we are using non-consumable electrode. This electrode is feed at the constant speed. Here electrode does not need the feeding. In TIG welding, no feeding is required because the electrode is non-consumable. Here DC RP is famous. Here AC and DC current are using. In MIG welding, we are making the fast welding speed. Here, TIG welding, slow welding speed. Here, flux is not required. Shielding gas, argon and helium is commonly used for both the case. In MIG welding, can be done for 40 mm. TIG welding, it is lesser, 5 mm. Filler metal in the form of feed wire. Here, filler metal may or may not be used. So, this is the major difference between the TIG and MIG welding. Next, we are going to know about the submerged arc welding. In submerged arc welding, what happened? We are using the bare electrode. Bare electrode. That means it is electrode without flux. Electrode without flux is called as bare electrode, and the flux is used in the form of powder or granules. Powder or granules. So granular flux is used, so it has to be feed. You can see here, this is the flux. So it covers the entire arc and it forms the welding. This arc is produced by the bare metal electrode. Arc is submerged in the blanket of flux. It will the blanket of flux cover the arc and flux in the form of granules. Weld mild steel plates of 5 mm thickness is possible by using the submerged arc welding. Next is electro gas welding and electro gas welding and electro slag welding are used for welding thick metals. For thick metals, these are the famous process we are using. So this is the electro slag welding setup. You are having copper shoe plate on either side. This is the copper shoe plate and copper shoe plate, and the electro slag is pouring here. Because of the slag heat, the metal get heated and able to join. So welding is started by generating the electric arc and completed by resistance heating effect of the slag. So initially arc is used and finally the slag is come to the picture. With the help of slag only they are joining. So after some time, with reduced power supply will be given the automatic welding machine to control the feeding of the consumable electrode. With the help of slag heat, the metal can be joined. Hence it is called as electro slag welding. It is mostly used in pressure vessel like boilers like that, and welding in only vertical position can be done. In electro slag welding there is no horizontal position, only vertical position can be done. Heat affected zone is very high. So these two are disadvantage of electro slag welding. Electro slag welding only vertical position and more heat affected zone. Next we are going to see about the plasma arc welding. Plasma arc welding is plasma is nothing but it is the ionized gas. It is the ionized gas. With the help of ionized gas, the welding can be achieved. So it is two types: transferred arc welding and non-transferred arc welding. Transferred arc welding means we have to transfer the arc from the upper chamber to lower chamber. In non-transferred arc welding, it cannot be transferred. So it produces the temperature of 33,000 degrees Celsius. Next, thermite welding. This you can be observed in the railway track. So they are mixing the aluminum. And iron oxide in the ratio of 1:3, and magnesium ribbon is there to make the fire. So chemical reaction is take place. It is the exothermic chemical reaction. Exo means heat will be evolved. Exothermic chemical reaction take place. So heat is produced. So it can be used to weld a rail, large gear, broken teeth and broken casing. So these are the things which are welded by the thermite welding. Thermite welding means it has to be two mixtures are mixed, aluminum powder with iron oxide. So it produces the exothermic reaction, it produces the heat. Next, resistance welding. In resistance welding, what happens? The heat is generated with the help of resistance, H equal to I square R T. So this is the Joule's law of heating effect. By this much of heat is produced. So those heat is used to weld the metal. So when two plates are welded by pin-pointed electrode. So this is the pin-point electrode connected to the transformer. So this is the transformer. So here the resistance is formed and able to join. So it is single spot welding. Similarly, multi-spot welding is also there. Multi-spot welding is called as projection welding, and continuous spot welding is called as seam welding. Continuous spot welding is called as seam welding. Multi-spot welding is called as projection welding. You can see here multi-spot welding, projection welding, continuous spot welding, seam welding. This welding process used for the automobile fabrication. For automobile fabrication, it is mostly used. So it has a low voltage and high current. So you should be remember. The resistance welding has low voltage, high current. Arc welding has high voltage, less current. Resistance welding has less voltage, high current. So this is the major difference between the arc welding and resistance welding. The arc welding has high voltage, resistance welding has low voltage. You can observe the seam welding. It is welded by the rollers. This is a projection welding where multiple projections are made. This is a flash butt welding. It is fixed clamp. It is a fixed clamp and a movable clamp. So both are heated by the resistance, so air resistance, and combined together to form the connection. That is the flash butt welding. Next is forge welding. Forge welding is used only for wrought iron. It is similar to the top. We have to heat from the external source and combine together to make the forge welding. Next, we should know about the soldering and bracing. Soldering is the process in which the parent metal is not melted, only filler metal is melted. This filler metal is called as solder, that is melted to connect the parent metal. This filler metal is called as solder. So it has to be melted, and which is used to join. So when the temperature is less than 450 degrees Celsius in soldering, in bracing, the filler metal is called as spelter. So here also only filler metal is melted. The filler metal is melted. It is a composition of copper and zinc. Here solder, it is lead and tin. So these two are the different process. The bracing is used only when the temperature is more than 450 degrees Celsius. In soldering is less than 450 degrees Celsius. So you can, here the flux used in soldering is zinc chloride, here borax and boric acid. So it is used in electronic industry soldering, and bracing is pipe fitting. So these are some of the difference between bracing and soldering. Next, we are going to know about the solid state welding. In solid state welding, pressure welding is used. It is solid state welding done at the room temperature. So it is the pressure welding. The next thing is explosive welding. With the help of explosive, the target plate and the flyer plate are bonded together. The large surface area contact are made by the explosive welding. The next thing is ultrasonic welding. Ultrasonic welding is used only for the brittle material. It can be used only for the brittle material. The ultrasonic welding can be only used for brittle material. It can be sonotrode. Sonotrode is vibrate, and with the help of vibration it can be joined. Next, friction welding. In friction welding, the drill bit and drill shank can be, the drill bit, this portion may be drill bit, and the shank, drill bit and shank portion can be joined together rotating tool, it has to be placed in the rotating tool. By friction, both can be joined in the solid state. This is electron beam welding. The electron beam is passed through the focus lens and it has to be welded. It has to be done in only vacuum. It has to be done in only in vacuum, because then only the electron able to pass it. So here we can get the high depth of penetration and the minimum weld bead is the precise control. So that is the advantage of electron beam welding. Laser beam welding, instead of electron beam, laser beam is fast. So it is a light beam. So it is used for the electronic industries. We can say that it can be used in the electronic industry. Here heat generation is very, very less. So these 2 points are, we should keep it in mind. In LBM, heat affected zone is less. Heat affected zone is less and it is used for electronic. Highly reflective material cannot be welded. So because it is a light, so reflective material cannot be welded. So laser welding is also called as micro spot welding. Friction welding can be suited for dissimilar material. And ultrasonic welding, it is used for fabrication of nuclear reactor component. Explosive welding is used for cladding of sheets. Electron beam welding can done only in vacuum. Plasma arc welding is also called as keyhole welding. Its temperature is 33,000 degrees Celsius. Here, friction welding can be used for tool shank and tool bit. Laser welding is used for electronic industries. So these are some of the points we should remember as per the competitive exam point of view. Next, welding defect. Welding defect, what are the welding defects it can be obtained? So we are having welding porosity is there, and the slag inclusion is there, incomplete fusion, weld spatter. Weld spatter occur due to the high weld current, and incomplete penetration occur because depth of welded joint is insufficient. And we are having underfilling, it occurs when the joint is filled with the proper amount of, when the joint is not filled with the proper amount of molten metal. When the joint is not filled with the proper amount of molten metal, it is underfilling. So these are the weld porosity occur due to the atmospheric gases. Slag inclusion occur due to the oxide flux and of the electrode coating material. Slag inclusion, incomplete fusion occur too fast travel of torch. Weld spatter occur high welding current and low welding speed and arc blow. These are the 3 reasons for the weld spatter. So current is high, speed is low and spatter. These 3 reasons for the arc blow. So because of the weld spatter occur because of these 3 reasons. So weld spatter is an important question as per the competitive exam point of view. Cracks, this inclusion and some other defects also there. We are having inclusion and lamellar tears, cracks, undercutting. In cracks, cold crack, hot crack. So these are because of the hydrogen entrapment, cold crack forms. Because of this is the hydrogen embrittlement, hot crack is formed. So in this crack may be longitudinal transverse crater. So cracks are 5 types. So longitudinal transverse crater and underbead and toe cracks. So undercutting is formed, it occurs when the base metal melt away from the weld zone and consequent generation at the toe of weld. So this may be the cause the premature failure. Undercut cause the premature failure. So these are the reason for the welding defects. So it is corrosion because of the presence of residual flux. Weld spatter, high welding current and more arc length. Poor fusion, improper current. Porosity is the poor quality of the base metal. Hot crack is formed due to the sulfur and carbon content. Weld decay is usually observed on the stainless steel. This distortion take place for the improper clamping. Undercut occurs due to the Next we are going to see about the casting. Casting is the process of making molten metal, pouring the molten metal into the cavity to get the shape. That cavity can be produced with the help of replica. That replica is called as pattern. So first thing process that is pattern making, then core making, molding, melting and pouring, cooling and solidification, cleaning. These are the basic steps of the metal casting. Next we are having advantage of casting. The molten metal can flow in any small section. Any intricate shape can be produced, and it can be possible for ferrous and non-ferrous metal. The casting is cooled uniformly, so there is no directional property. So there is no directional property in casting. So in disadvantage of casting is poor surface finish, dimensional inaccuracy and defect arising out. So we are having pattern. Pattern is made up of material wood, plastic, plaster of Paris, wax. So we are having types of sand. We are having green sand. Green sand is the sand with moisture. Sand with moisture is called as green sand. Sand without moisture is called as dry sand. And the facing sand is to prevent the metal from the burning. Parting sand to separate the green sand from the pattern. Loam sand is nothing but it is 50-50. 50% sand and 50% clay. And synthetic sand, it is a sand made by artificially, so that the properties can be controlled easily in synthetic sand. Oil sand is used for core, and zircon sand has the higher bulk density and lower fusion point. So additives in molding sand, so we are having wood floor. Wood floor is used to increase the green strength. The starch is used to increase the resistance of deformation and the skin hardness. Iron oxide is used to add strength of green sand. Coal dust is used to surface finish. So these are the different things you have to remember. Wood floor, green strength, starch, skin hardness, iron oxide, green strength, odd strength of the green. So coal dust, surface finish. So these are things you should remember for the additives. Next, properties of molding sand. Refractiveness is the property, it's the ability of sand to withstand high temperature. Green strength, it is a property when it is mixed with clay, it has to possess some compressive strength, that is the green sand strength. Dry strength, it should be tested under the dry condition. And the hot strength is the temperature of the sand at the elevated at the high temperature. Permeability is the ability of the sand material to allow the gas during the casting. When the sand touches the metal, it forms the gas. That gas has to escape. The ability of sand to escape the gas is called as permeability. Permeability can be calculated by formula VH by PAT, where V is the volume of air passing through the specimen, H is the height of the standard specimen, P is the pressure of the air, Ca is the cross-section area of the cylindrical specimen, and T is the time required to pass the specimen. So next is collapsibility. After casting, when it is able to break, it has to be broken away. And the flowability, it is the ability of sand to flow like a fluid. Cohesiveness is the ability of sand to adhere together with the sand. Adhesiveness is the ability of sand to stick with the pattern board. So we are having types of pattern. Types of pattern is skeleton pattern is used in slow molding. Match plate pattern is used in the mass production. Single pattern is the pattern with the flat back. Split pattern, we are having two piece, cope and drag. Multi-piece pattern is the pattern with loose piece. Pattern with loose piece is called as multi-piece pattern. Gated pattern is the set of pattern arranged in the common gate. Sweep pattern is used to produce a symmetrical part. Segmental pattern is used to produce a circular shape. And metal pattern used in mass production. Loose piece pattern, when the pattern cannot be withdrawn, there the loose piece pattern can be used. So these are the factors governing the pattern material. So pattern material: wood, disposable pattern, thermoplastic pattern, thermosetting plastic, and plaster of Paris are the pattern material. So elements are produced in the pattern. Those elements are machining elements, raping elements, distortion elements or camber elements. So machining elements, it for the machinability. After casting we have to do machining, so we should make some positive, so for finish purpose. Raping elements, when we shake the dimension when we shake the pattern the dimension varies. For that we have to produce the raping elements or shaking elements. Shaking elements is the negative elements. And distortion elements, for distortion element U shape, V shape like object, the some excess amount of material is in the form of distortion elements. So it is particularly for U shape, V shape and flat object, this distortion elements will be provided. So draft elements is the taper provided on the taper provided for easy withdrawal. So that elements is called as draft elements. And sinkage elements is the compensation for the solid contraction. Compensation for the solid contraction is the sinkage elements. So we are having three types of sinkage: liquid sinkage, solidification sinkage, solid sinkage. This solid sinkage can be take care by pattern, these two sinkage take care by riser. So this is a setup of the casting where it has to be poured into the pouring basin. It has to be poured in the pouring basin. Pouring basin. After pouring basin, it has to come to sprue. Sprue is the conical passage, and it has to pass through the runner. Next runner, and then mold cavity. So pouring basin, sprue, runner, mold cavity. So we can say that we can draw the diagram in this way. It is a sprue. So this one is the pouring basin. So here it is runner, and it has to come into the mold cavity. So after mold cavity, it will come to the riser. It has to be come to the riser. So this is the entire setup of the So this is the pouring basin, sprue, runner, gate, mold cavity, this is riser. Okay, so these are the setup we should remember. The pouring basin is act as a reservoir. Sprue always in the form of conical shape to avoid the aspiration effect, because when it is not conical, the air may get into enter. Runner is the horizontal passage. Runner is the horizontal passage. Gate is the entry point. Gate is the entry point. This is the entry point where the metal get into the picture. So chaplet are used to support the core. Chaplet is the part which is used to support the core. To support the core, here we are placing the core means to support the core. To support the core, this is the core. When it is core means to support the core, we are having chaplet. So this is the chaplet. Chaplet is the external iron pieces. Chills are used for desired cooling rate, uniform cooling rate. Chills are used. Chills are used for desired cooling rate. Riser is used for reservoir for molten metal during casting, provided in the casting, so that when it is shrink, the compensation of the metal can be made by the riser. The compensation of metal can be made by riser. So you can easily, the top flask is called as the top flask in the casting. This is called as scope, and the bottom flask is called as drag. So riser is used as a reservoir for molten metal during compensate for the shrinkage. Pouring basin, it is a reservoir for molten metal at the starting point. And the sprue hole is the feed molten metal. Skim bob is attached to the sprue. Strainer core, filter. The strainer core is a filter. Gate is the opening. Gate is the opening where we are feeding the casting. Next we are having gating ratio. Gating ratio is the ratio of sprue, runner, gate. So S or G you can easily remember. 1:4:4 for non-pressurized casting, and for pressurized casting 2:2:1. So this is for pressurized casting. So for different types of the casting may be classified into pressurized casting and non-pressurized casting. For both the things, we are having different gating ratio. Next, we are going to discuss about the Chaurinov rule. What do you mean by Chaurinov rule? Chaurinov rule is the Chaurinov's rule. Chaurinov rule. It is says that solidification time is proportional to volume square. Solidification time is inversely proportional to area, surface area square. So we can get T is proportional to V by A whole square. So this is surface area, and T equal to solidification time constant V by A whole square. So this is the Chaurinov's rule for the solidification time of the casting. By using this, in all the competitive exam, the problem will come. Next, we are going to see about the classification of casting. In the classification of casting, we are making the temporary mold for sand casting, cell casting, investment casting, full molding, CO2 molding. For all those casting, temporary mold is there, but permanent mold is for centrifugal casting and die casting. And another, so we are having three types. So we are having permanent mold. So it can be classified as permanent mold casting, temporary mold casting. In temporary mold, sand casting, shell molding, investment casting, full molding, CO2 molding will come. In permanent mold casting, centrifugal casting, die casting and sludge casting will come. The shell molding, we are using bakelite resin. In shell molding, we are using bakelite resin. So bakelite resin is nothing but phenol formaldehyde. This phenol formaldehyde resin is used in shell molding along with the fine sand. So because of this fine sand, this process is costlier. So these two are the important thing it should be remembered in shell molding. In investment casting, what we have to remember, we are using the wax pattern. Instead of normal pattern, we are using the wax pattern. So it is a complex profile can be made by using in the investment casting, the complex shape can be made. So gas turbine blade, like that we can be formed, and making jewelry and surgical like that. So investment casting, it can be used for that purpose. Die casting, we are having a die. It may be hot chamber die casting. And cold chamber die casting. So hot chamber die casting means, so melting pot is inside the melting pot. This is a melting point inside the furnace itself. Okay, and the cold chamber melting pot is separate and die will be separate. Die and melting point together in the hot chamber die casting, and the cold chamber die casting, the melting point is keep it separate and the die area will be keep it separate. The hot chamber die casting is used for only low melting point alloy. Okay, it should be noted. The hot chamber die casting is used for low melting point alloy. So this is the difference. Melting chamber is the integral part in the hot chamber die casting, and cold chamber it is separate. So low melting point is you can observe in hot chamber, and high melting point here less dense and porous casting is produced, and there in cold chamber more dense casting is produced. So here production rate is faster. Here production rate is slower. So low melting means zinc, lead, tin. Here aluminum and magnesium, it is a cold chamber die casting. So next is centrifugal casting. To produce the centrifugal casting is used to produce the pipes. So it has to be rotated. It has to be, the metal will be forged and it has to be rotated. It forms the cast iron pipes. The pipes may be easily produced by this method because of the centrifugal force. So what happens? So here the dense structure will be formed. So it is dense structure will be formed, so it is difficult to machine. The metal formed, the shape formed in casting is difficult to machine. So difficult to machine in the centrifugal casting. So this is the important point. We are having semi-centrifugal casting is here. In semi-centrifugal casting, the process mold is placed on the horizontal plate. So it is on the horizontal plane, but centrifugal casting is on vertical plane. So that is the main difference. Here it is horizontal plane, there that is vertical plane. So in centrifuging, we are having a central chamber. From that we have spokes like arrangement. So it has to be cast in the different spokes. So center feeding metal here, pour here, and when it is rotate, the here casting will be made, here casting. So 4 casting, 1, 2, 3, 4. 4 casting is produced at a time. That process is called as centrifuging. So these are the different significance of the different process. Fit molding is used for large. Machine molding is used with the match plate pattern. Low molding is used with the skeleton pattern. Sand casting is used for parts tendencies to warp. Cartier process. We are having separate processes called as Cartier process, where plunger is used to feed the molten metal. Antioch process is used with the porous mold. And pressed casting are used for ornament. Slush casting are used for ornaments. Continuous casting is used to make the slab. Continuous casting is used to make the slab. Centrifugal casting is used to make the pipe. Semi-centrifugal casting is used for water pipe of large length. Centrifuging is a process in axis of rotation does not coincide with the axis of mold. The axis of rotation, because axis of rotation is here and axis of mold will be here. So we are having axis of mold, it is here, and axis of rotation is here. So both are the points does not coincide. In carbon dioxide casting, we are using sodium silicate. Carbon dioxide molding, we are using sodium silicate and clay. So this is the composition we are using for the CO2 molding. Slush casting is used in to produce the statue, hollow statue like that. Shell molding, thin sections can be manufactured. So this is for statue, hollow statue can be produced, and shell molding thin sections are produced. Plaster mold casting, mold is prepared by gypsum. So it is used for non-ferrous metal. And investment casting, it is a lost wax process, is used the wax pattern. So these are some of the process it has to be remembered for the competitive examination point of view. Next we are going to discuss the flogging. What do you mean by flogging? Flogging is the removal of sprue and riser. Drossing. What do you mean by drossing? The formation of oxides in the molten metal is the drossing. And fettling. Fettling is the removal of extra material from the casting. So these are the common tests, destructive test and non-destructive test, which can be done for the casting. It is tensile test, fatigue test, hardness test, wear resistance test. Those are the destructive tests. After that, no component will be there. Non-destructive test, ultrasonic test, radiographic test, dye penetrant test, magnetic particle test. So odd tear defect can be found out by radiographic test, internal crack, ultrasonic test, subsurface crack, dye penetrant test. So these are tests used for the casting. The next topic is casting defect. In casting defect, the famous defect we can observe is, so it may be gas defect or molding material defect or pouring metal defect, metallurgical defect. So we have to know that this is a swell. Swell is formed due to the enlargement of casting, and a cold shed is formed. It is because of the two streams of the metal. Because of turbulence, what happened? Two streams of metal are too cold to fuse. When two streams are come here like this, but before it come, it is two streams of metal are too cold to fuse. So that defect is called cold set. It is two streams of metal are too cold to fuse. Next is blowholes. Blowholes, because of the less permeability, the gas cannot able to escape, so it will form the blowholes. Porosity is the fine holes. When you, after machining, you observe the fine holes inside the casting, it is called as porosity. And distortion is the swelling in the surface. Scab are the due to the warty excretion. Scab are produced. So next is art tear. Art tear is formed due to the hindered contraction. Art tear is formed due to the hindered contraction, and misrun is formed due to the low fluidity. Because of it will form like a line. So low fluidity, a line met but not fuse. Rat tail is the V-shaped grooves are formed on the surface. These are the some important casting defect. It should be remembered for the casting purpose. We have covered the 5 days class for the metal cutting and machining operations. So we have covered both the theoretical part and problematic part in a elaborative manner, and we also discussed some of the basics in engineering material and metal welding and metal casting process along with that. So it will be useful for all the students, so you can practice the problems and improve the skills of your manufacturing technology part. So this is the important part in the GATE point of view and engineering service point of view in all the competitive exam. So prepare well, students. All the best for your preparation. Cheers.